Hello there. Going to look at nebulae today and how that links to the life cycle of a star. So mainly looking at the birth of a star and how that carries on through to the eventual death of a star. So all stars are doomed to die, I suppose. So here's an example of some nebulae. A nebula is, well, it used to be used as a phrase to just mean a fuzzy patch of light in the sky. And obviously, as we've got better magnification, we've seen them more clearly, been able to tell the difference between them. But here's examples of some of the most famous ones. There's the Crab Nebula and the Pillars of Creation, I think, on the left there. So, this was originally a catalogue of fuzzy patches of sky put together by Messier, known as the Messier objects, and obviously with colour we'll see a bit more detail, but you can see that they're not just random fuzzy patches of sky, and there's a difference between them. So there's galaxies, there's clusters, there's nebulae in there. So the term nebula went away from being used as just a fuzzy patch of light in the sky to a big cloud of dust and gas, and some of these are incredibly big. So the originally galaxies and clusters would have been coined nebulae, but they're not anymore. There we go. So nebula, definition of nebula is a gas and dust cloud. So that was single sentence on the bottom there would be worth noting down if you want to pause the video. So there's different types of nebulae. Now while this isn't on the course, it will be worth giving a mention too. So there are three types that are linked with the birth of a star: emission, absorption, reflection. Then there's two types, planetary and supernova remnants, which are linked with the death of a star. Here's some emission nebulae, shine very brightly. Here's some absorption nebulae. Reflection. So those are the three linked with stars starting to form inside there. Huge clouds of dust and gas, gravity playing a role inside there, trying to clump together bits of dust and gas, and as it does, as it gets bigger and bigger, these clumps and all the matter is accelerated faster and faster as that clump becomes more dense. Then it smashes in, eventually you reach a temperature where fusion can begin and you've got yourself a star. Now the planetary nebulae and the second one, which is linked with star death, are more kind of classically formed in terms of big round things than you can see, because they're from an explosion. So planetary nebula very often have a clear central point, and bigger stars, when they die, you're left with a supernova remnant. Very famous Crab Nebula there. Although, can you see the turtle? I like the turtle. There's the shell and the head. Two little feet there. The crab, this is the shell of the crab, the pincers there. Can you see an elephant? Elephant charging towards you. Look, there's the trunk. Isn't it good? And head, there's the big ears. Get the idea. Yeah, you might want to find something else. I don't know. Let me know. So, that's what I've tried to summarize for you. But essentially, the beginning of the story for the life cycle of a star is with a nebula, and the end of the story is with nebulae as well. So, clusters we're not doing about, but it would have originally been thought of as just a big cloud of dust and gas. But you can get stars forming in big clusters. They can form together. You've got open clusters and globular clusters as well. But we'll race through that and we'll get on to the life cycle of a star. So what will it be like? Well, it actually depends on the size of the star. Stars work in the opposite way to your taps for their temperature. So a hot tap is red and a cold tap is blue. A hot star is blue and a cooler star is red. Now, we use this classification system, OBAFGKM. The M stars are the cooler stars and the blue stars are the hotter stars. The hotter stars are the bigger stars. You can think of it almost like a rainbow. Red, orange, yellow, Yeah, green doesn't work. You kind of, and then blue, and you go, right, yeah. But essentially, we got the blues, yeah, and we got the red, orange, yellows. The green has loads of red light, but it also has loads of blue light. So if you all mix all the light together with even amounts, you'll end up with white light. So because green is in the middle, that gives you white light. So essentially, you've got your red, orange, yellow, white, blue. I'll just go with the blues there. So the bigger stars actually, in answer to this question, will live a much shorter life. They burn out much more quickly, and the smaller stars last for longer period of time. Our good old Sun is a G-class star, so we're quite small compared to the larger stars. And when our Sun dies, it will not go in a massive supernova. So what will be left over for us is a planetary nebula, not a supernova remnant. Okay, these letters you do have to you have to know a little bit about them. These are known as the spectral classes. O, B, A, F, G, K, M. There are different ways to remember it. One is not a very pleasant way, so I'm not going to share it on the video, but you could come up with your own rhyme to remember the order. Alright, there we go. So, life cycle of a star. We've said it starts with a nebula, and then the force of gravity brings clumps of it together. In a nebula, by the way, it doesn't have to just form one star. You can have millions of stars forming in massive nebulae. So you start to get a protostar. Now, you need to know what a protostar is in terms of the fact that it has not yet begun nuclear fusion. So, yes, you need a little diagram showing the life cycle of a star. This is from GCSE. But you also need to know a bit more information about each stage. I suppose at GCSE, the questions normally focused on, do you know the order of the life cycle? Could you say what comes after what? But at A level, very often you're describing a particular part of that life cycle. There's not a great deal to the protostar, though. Key things I would note down is a protostar. Nuclear fusion has not yet begun. So matter is clumping, it's going to be a star, but it's not yet got hot enough to cause nuclear fusion, so it's not yet a star. Eventually it will get hot enough, and it will enter where it spends most of its life, its main sequence stage, which is where our Sun is now. And that's how it spends 90% of its life. Nuclear fusion doesn't happen throughout the entire star, it happens in the core of the star. Now, after the main sequence, you'll get an expansion. Now, I know that the red giant, you've got the red supergiant on the right and the red giant on the left. It's not to scale. You can see the Sun there, but to the left of the red giant. So it swells up. Now, it seems strange. You might think in classic terms that a star will run out of fuel, and then it will shrink. You would think it would just shrink away, it would disappear because it runs out of its fuel. And yet it expands. That would seem to be a sudden increase of energy as it's running out of fuel. So we'll need to understand why after a main sequence it swells up massively. What causes that? What's at play with the forces? Okay, and then after that, you'll be left, as I mentioned, so something like our Sun will go to a red giant, and then that will be left with a planetary nebula. So after the explosion, this is all the stuff that's come from our Sun, and at the centre will be the leftover white hot core, no longer doing nuclear fusion, so essentially just a hot rock, and that's known as a white dwarf. If you have a much bigger star than our Sun, though, that will go supernova. The most energetic thing in the universe, a supernova explosion. That's where all the heavier elements in the universe are made. Anything heavier than iron, the only place it can be made is in a supernova. At the centre of a supernova, or the supernova remnant that's left over, you will have one of two mysterious objects. The pulsar, otherwise known as the neutron star, or the black hole. So essentially, a star always starts as a nebula, and it always finishes as a nebula, but there's something exciting in the middle of that nebula. It's either a white dwarf, a neutron star, or a black hole, and that's in order of the size of the star. So the biggest stars give you a black hole, and the smallest stars, like our sun, give you a white dwarf. Now, the only other thing to add on to that after that is a black dwarf. A white dwarf will eventually cool to form a black dwarf, but we don't think the universe is old enough to have any black dwarfs in. Alright, here's the two mysterious objects. That's the black hole and the neutron star, which we will do. We will learn more about in coming lessons. So, skip that. Here we go. So, just to summarize, we go from a nebula to a protostar to a main sequence. The main sequence now. So, I gave you a bit more information. I mean, all you need to know about a nebula is that it's a big cloud of dust and gas. All you need to know about a protostar I've given you already, but you do need to know a fair bit about the main sequence star and what happens when it starts to swell. Okay, so this is the key thing about the main sequence, and it was required to know this at GCSE as well. Main sequence is a battle between two forces: the force of gravity trying to collapse this big ball of gas in on itself, and the force pushing out, which comes from the nuclear fusion taking place in the core. So the core, the very bright yellow bit in the middle, that's the only place nuclear fusion is taking place, and that creates a force pushing out. So there's a balance there between the inward force of gravity and the outward push from the fusion, and that's the main sequence. If the nuclear fusion, that force from nuclear fusion changes, then it won't be stable anymore and it won't be in its main sequence. Okay. So what happens over time? Oh, well, actually, I'll explain it using this slide. So what happens over time is eventually the fuel in here, the hydrogen, which is fusing into helium, will start to run out. So there will be less fusion. So, even though I've said it expands, it does collapse. It collapses in on itself for a fairly brief period of time in comparison to the life of a star. But you should remember, hopefully, from GCSE and gas laws, or maybe that you've done this year, that if you compress a gas, it will heat up. So when the star collapses, it's like compressing a gas. It heats it up, and now all the fuel that was outside of the core, maybe not all of it, but a lot more fuel, reaches a temperature hot enough to cause nuclear fusion. So all of a sudden, because it's collapsed in on itself and heated up, the nuclear fusion starts in places outside of the core, and there's a whole load more fuel there, so it suddenly becomes loads more powerful and expands to a great size. When our sun goes to a red giant, we think that it will go further than the Earth. It will expand past where the Earth is, so the Earth will be eaten up by the red giant that is the sun. So, this is the that was from a Simpsons episode, but yeah, let's look at the chemistry behind it here. So here's your periodic table, and as we go through, you'll eventually reach iron. Now, iron is the most stable element in the universe. From your nuclear physics, you might be aware of that. It's got the highest binding energy per nucleon. So actually, to fuse hydrogen to make helium, and to fuse helium to make the other, and as we go up, you will be releasing energy. But to fuse iron or anything higher than iron, you'll actually absorb energy, which was no good for a star because it wants to be giving out the energy and fighting gravity in that way. So iron is like a poison to a star. It would spell the death for that star. Now, at the moment, about 74% of the universe is hydrogen, about 24% is helium. So what you have is hydrogen, and hydrogen will fuse to form deuterium, and then it will fuse with another proton to form tritium. You're wondering how, there's no neutrons floating about on their own. Neutrons are very unstable outside of the nucleus. So when two protons join, one of them will straight away turn into a neutron. And then deuterium will join with tritium, the fusion reaction, energetic neutron fired off, and you're left with helium. Okay, so two different isotopes of hydrogen join, and you get helium that way. So here's helium, lithium, carbon, and our sun will only ever get hot enough to do this. So you might get up to carbon, but it will never ever reach temperatures hotter than is required to get past carbon there. But other stars, as I've said, can get all the way up to iron, but never past it. So these are the key notes from the main sequence. The main sequence, life will come to an end when it's run out of its hydrogen in the core, and then it will lose its battle with gravity. So once it loses its battle with gravity, it starts to contract. That heats it up anytime you compress a gas, which allows fusion for the outer shell, the outer layers. And that causes a rapid expansion, and it's now entered its red giant phase. So, this is the, just artist's impression really. So the sun will get very large, but it will actually eat up the Earth. So yeah, get a bit more dramatic. There it is. There's a lovely painting of the death of our Earth for your enjoyment. There's a picture of the sun, a picture of a sun as a red giant. A lot bigger than the last one, isn't it? Not quite sure on the scale there. Anyway, so you'll be left over, well, what will be left over is the centre of it, which is the white hot core, and that's the white dwarf. Just a hot rock in space, really. It's only white because it's hot. It will eventually cool. Take a long time to cool down. So this is where we believe our sun is about now, about 4.5 billion years into its life cycle, and then after, it's about halfway through, isn't it? Red giants, and then it'll all happen rather quickly. In comparison, you don't need to know all this stuff. So bigger stars, the O class, the B class, they'll get past it. So they'll go from hydrogen, helium, carbon, neon, oxygen, silicon, and then iron. But as I said, that's like a poison to a star. So when that dies, it will go red supergiant, but kind of the same reasons. And then you get supernova. I put an exclamation mark in there because it's the most energetic thing in the universe, so I thought it was worthy. And I for the 2-year course, I save up my exclamation mark for this very point. Okay. So what about the other elements? Gold, for example. You've got uranium there. They can only be made in a supernova. The fact that we have elements on this Earth heavier than iron means that we have come from a supernova. There was a giant star that existed that has exploded in a supernova, and from the nebula that was left over, our solar system has formed. And we know that because our solar system has elements heavier than iron. So, here's the story carrying on. So we have a nebula into a protostar, which goes into a main sequence star, then red giant or red supergiant, and then the red giant goes to a planetary nebula, and the red supergiant will go to a supernova explosion and then a supernova remnant. What's left in there? Well, two very mysterious objects. So the lighter of the two will be the neutron star. It pulses, you see. It's a very strong radio emitter. Now, if it is aligned in such a way, as it turns, we get to view the poles of it, every spin, then it will pulse at us. And, they can pulse hundreds of times a second. And those are, it was Jocelyn Bell, I think, did a huge amount of work. She's from Northern Ireland. And these are neutron stars that it's just neutrons. So the electrons and the protons have gone. Now, you might remember the fun fact that you learn in physics that the universe is mostly empty space. When you learn about the plum pudding model being disproved and Rutherford finding out that the atom was mostly empty space, so therefore the universe is mostly empty space, then um, we could fit every human, if you remove their empty space, into a teacup. Well, this has removed the empty space. So essentially, the teacup would weigh the same weight as all the people on Earth, and that is the density of the neutron star. So yeah, a teacup worth would weigh as much as everybody on Earth. So it's incredibly dense, unbelievable. The gaps have gone, essentially. Spins incredibly fast. The reason it does is if you've got a spinny chair in your room, then you should stick your legs out and spin. Try not to hit anything. I'm not telling you to do. I take that back. I'm not telling you to do that in case you sue me for a big bad injury here. But if you were to do that, imagine yourself doing that, and bring your legs in as you spin, and you'll find yourself go faster. Well, imagine a massive star contracting to a 20-kilometer diameter. That's a pretty big contraction. So imagine how fast it ends up spinning, and that's why it spins so fast. So it's the size of central Manchester, I believe. Really fascinating things. They pulse very strongly. They're highly magnetic. And then you have the black hole, always used in sci-fi. And the black hole has become so dense that light can't escape. Now you need a little bit of a better explanation for A level, but it really is typically just 2 marks to find what a black hole is. But essentially what we'd say is the escape velocity is equal to the speed of light at the surface of a black hole known as the event horizon, or greater than the speed of light inside the black hole, but we will study that in more detail when we look at black holes. Okay, so I've kind of mentioned that about the spinning and then black holes. Now luckily a small percentage of them have these huge jets which we can detect anyway. And so black holes, I think 30, 40 years ago there was they weren't as accepted as they are now, and it took time for black holes between them being theorized to people thinking, well, we'll never be able to detect them because they're black and they don't emit anything, they just absorb everything, and now they're easily detected, which is a breakthrough. And Stephen Hawking did a lot of work, that Hawking radiation and the detection of black holes there. Which leads on to trying to classify these stars and put them into some sort of order. Now this is not for this lesson, this is for another lesson, but this is known as a Hertzsprung-Russell diagram. So what we've got all the O-class stars and the M-class stars and the K-class stars, and we fit them all onto a nice little chart which we will study in the coming lessons. The Hertzsprung-Russell diagram is something that is important to understanding the life cycle of a star, but it plots the life cycle of a star onto a little chart like this. Okay, so from this lesson what you should take is the revision, I suppose, if you did separate science, of the life cycle of a star. So a little diagram which would say, at the top you could have nebula, arrow going down to protostar, and then an arrow going down to main sequence, and then we'd have 2 arrows that branch off down left and down right. Down on the left would be your it goes from the main sequence. So for the lighter stars you have the white dwarf, and then it would go into a black dwarf. But then for the heavier stars you would have supernova, followed by branch off again, 1 left, 1 right, which would be a neutron star or a black hole. So they're the different options. And in GCSE you often get asked describe the life cycle of a star like our sun, or describe the life cycle of a star much heavier than our sun. So that tells you whether you're going down the left or down the right. So you need to know the order, but you also need to know a bit more information. So you should be able to answer the question, what's the difference between main sequence and a protostar? What is a main sequence? There you're just talking about the balance between the force of fusion and gravity pulling in. Why does a main sequence turn into a red giant? So what causes it to expand? Or what causes it to end its life cycle as well? Why? How are elements heavy in iron created? How does nuclear fusion occur in a star? So just a bit more information, and then of course there's not much to say about a white dwarf. It's just the leftover core of the star, but we do need a bit more information on the neutron star and on the black hole, which we'll deal with in another lesson. Okay, and then of course after this we'll go and look at Hertzsprung-Russell diagrams, which classify these stars in a way for the spectral classes against their luminosity and temperature as well. Thank you very much. I hope that was helpful, and I will leave it there for today.